another statistical class, and I also want to welcome you to new month of October. Um, Before now, I've walked you through some kind of topics, and we know we've already finished our clustering, and we're actually moving into another topic. But before I move forward, I want to I want to make a few announcements. Number one, um, if you have been sending message to me through the email and you didn't get your reply in 24 hours, then your email didn't get to me. So what I would advise that you should do is, if you wait for 24 hours and you don't get my reply, please text me on my number. So I think I'm gonna write, give me 1 second. Give me 1 second. So my number is 763-501-6180, and the number is on the what is it called? It's on the course canvas, so you can text me a message. That is if you wait for 24 hours, because I teach a lot of classes and there's possibility some messages may not be delivered. Okay, I want to welcome you to this topic. This topic is very crucial. It's called principal component analysis. We're also going to, apart from doing it today, we're also going to talk about this tomorrow. I'm sorry, on Friday. So what I just want to do today is just to tell you the essence of principal component analysis, to also walk you through some mathematical properties of principal component analysis. Now, in the outline, I'm going to tell you the motivation behind that. I'm going to tell you the criteria of principal component. I'm also going to talk about the properties of PCA. Okay, so I just wanted to pay attention while we're doing that. Okay, so let's start with the motivation. Let me tell you this. We live in a world where we normally want to investigate, want to talk about investigating pattern, we want to talk about whether in a medical line or in economies, in environment, in security, and so on like that. We normally work with high dimensional data set. We normally work with complicated data set. And the reason for that is because, when we're collecting our data, we normally collect data over so many variables. And what and having so many variables, it's actually going to take a lot of time, trying to understand what we want to figure out. And we don't want a situation where we're going to be consumed by problem. When problem arise, we don't want to waste time. We want to quickly get things done. And what are we going to do? What we can do is, if I have data set that is of high dimensional, that is of dimensional, is there a way we can reduce it? We can reduce the dimensionality in the data set. Reducing the dimensionality in the data set in such a way that it's not going to it's not going to result into what I call total loss of information. So is there a way we can reduce something? So the essence of reducing something, number one, is because we don't have unlimited data storage. Does that make sense? We don't have unlimited data storage. Is there a way we can reduce what we're going to put in the space? That's number one reason. Number two reason, if we have so many variables, so many features, okay, it will be very difficult for us to learn things quickly with so many features. And that is the reason why the idea of a principal component analysis is actually needed to reduce the dimensionality in my data set. And while reducing it, we don't want to lose significant information. Can we have a way to retain some valuable information? Okay, and that is why we make use of principal component analysis. So the major intention is to reduce dimensionality. Okay, so of course, you're actually going to collect data set from and sample, and each of the objects in the sample, you're going to collect data on so many variables. That's it. I call it x1 up to xp. Okay, so and what we now want to do is we want to be able to reduce the original dimension for so that the original dimension, we're looking for a way to replace the original p variables with k variables. I'm going to say that again. We actually want to make sure we reduce the original original p variables, okay, to k variables. That k variable is less than p, okay, which means at the end of the day, we're actually gonna be working with a reduced features. The reduced features that we're gonna set away at the end of the day as retain significant information. Okay, so that is exactly what we mean. And the idea that's going to be the principal component analysis that we want to talk about, it belongs to the class of linear projection method, because at the end of the day, the new variable you're going to have, okay, is still going to be a linear combination of the old variable. Okay, the new variable that you're going to have is going to be a linear combination of the old variables. Okay, and I'm going to show you how that's actually going to work. And let me also tell you this: the reason why we always want to reduce is because for visualization's sake. It is very, very easy to visualize a project in 2D or 3D the moment you have, a complicated dimension that's going to be problematic for visualization. That's another reason. Okay. Now, so that is our intention. And we use this approach most of the time, whether, in classification, in regression analysis. Okay, just wanted to take notes of that. Okay, now I think before I'm actually going to walk you through this, let me first give you an example in real life. Because let me tell you this, I understand my statistics perfectly. I understand my mathematics perfectly, because I actually link whatever statistical content or equation or notation to real life. So the moment I understand that in real life, I actually understand what I'm going to be doing mathematically. Now, this is what I'm trying to say. In image compression, we use principal component analysis. Why is it that we need that? Why do we need? Why do I need to compress my image? We need to compress image. Don't forget, the image is in dimension, right? The image is in dimension, right? And the dimension represents the numbers of pixels. The numbers of pixels, don't forget storage. We talk about storage facility. We don't have unlimited storage facility. The more pixels, the more data. I'm going to say that again. The more the number of pixels in image, the more the numbers of data point, then it actually means you need more storage space to be able to accommodate that. Now the question now, I don't want to pay more money to get storage space. Don't forget, in research, we're limited by budget, even though we're also looking for efficiency. What can we do? Can we have a way to compress the image that I have, but I'm actually going to compress this image without losing significant information. The new image that I'm actually going to have that I call a compressed image, there will not be a total, there won't be a significant difference between the compressed image and the whole image. That's what we mean by image compression. And you know what? We're actually going to use principal component analysis like on Friday. On Friday, Friday lecture is dedicated to how do we do this now when we have data set? How do we do it? What we're doing now. I actually want to walk you through how we do that mathematically. I mean, try to unravel the mathematical principle around that. That's what we want to do now. But I'm trying to first, like, let me talk about the area of application. Now, that is image compression. I just told you now. Why do I need to compress my image? It's because of storage, data storage problem. That's why I need to compress that. Number two is what we call face recognition. Okay. And that's why when I see those who work with security, I always respect security personnel. Okay. If you are not smart, if you are not statistically inclined, you may not be able to work with any security apparatus. There's something that we call face recognition. Do they need to know everything about a criminal before they can actually bring a criminal to book? No. They can just, what are the significant features of a suspect? Sorry, I'm not going to say criminal. I'm going to say suspect for now, because when somebody is alleged, is presumed to be innocent until the courts actually prove otherwise. Now, before they can actually trace this particular guy, okay, this guy, not me, this guy, I'm talking about this phone right now. Let us assume it's a person before we can link this guy to a crime. The security personnel does not need to understand everything about the guy. They only need to look for some significant features. And that is the reason why the idea of a principal component is using face recognition. And in principal component, you're going to see us applying something you've done before, agent values, agent vector. Because we're going to talk about agent phases in face recognition. Does that make sense? Because the agent values in principal components is going to talk about variance maximization. Now, don't see variance as an issue in principal component. In statistics, generally variance is an issue, right? But in principal component, variance talk about maximum information. Does that make sense? Okay, I think I've talked about application in image compression, face recognition. It also have application in medical field where you want to understand a patient. And at times we do scan, right? They do scan X-ray, okay? And when you look at the picture of the X-ray, that is not the original. Let's say if they do X-ray of heart, okay, that picture is not going to give you the exact occurrence in the heart, something, but that picture is expected to extract significant pictures that will enable you to understand what's going wrong, what is wrong with the patient. So we use idea of principal component in medical analysis. What about in genomics, where researcher, there's something that we call genome-wide association studies, GWAS, where researchers want to understand the genetic structure in the population. Maybe they want to use the idea of clustering. They want to cluster individual with the same genetic structure. And there's so many, because what you talk about, there's so many variables when it comes to gene expression, thousands of variables. We don't have time to study all of that. The idea of a principal component analysis can be brought in to reduce the dimension of that, to ensure at the end of the day, the reduced features that we're actually going to set up with, that we're going to head up with, will do the job. Okay. And finally, I'll talk about the application in energy generation and distribution. At times, the utility company want to understand the pattern of energy consumption in a population, could be from individuals or from businesses, and there's a lot of variables involved. And at the end of the day, they're actually going to end up with some features that will enable them to understand the way consumer actually use energy in the population. Okay, now now I've given you enough information right now. Even in finance, okay, in finance, there's a lot of information going on in market. There's so many variables. Okay, we're actually going to use the idea of principal component to be able to identify key important economic factors, okay, that are needed for us to be able to understand the stochastic behavior of returns and so on like that. But you know what?